Hello everyone! Today I'll be discussing our paper, Explaining in Diffusion, which was accepted into CVPR 2025. This work was completed by Tahira Kazemi, Ritika Alada, and Pinar Yanardog at Virginia Tech. Classifiers play a critical role in computer vision, powering tasks across a wide range of domains. But despite their effectiveness, it's often difficult to understand why they make certain predictions. In the past, researchers have turned to methods like GAN-generated counterfactuals or heat maps to pinpoint features influencing a classifier's decision. While useful, these approaches come with limitations. They often require additional training or depend heavily on manual interpretation of the results. Diffusion models, on the other hand, offer a new and promising direction. They're capable of generating high-quality, diverse images, but so far, they've lacked the tools to automatically extract and rank meaningful semantics for explanation. In this work, we aim to solve this problem by using diffusion models to identify and rank these key features that influence a classifier's decisions. Specifically, we introduced Diffx, a novel, training-free framework that leverages diffusion models and vision language models to explain the decisions of classifiers. At its core, Diffx uses a vision language model to build a hierarchical semantic corpus, capturing concepts across multiple domains. It's designed to handle everything from single concept classifiers to those dealing with complex scenes. Compared to previous approaches, Diffx produces clearer and more detailed explanations, offering deeper insight into what drives classifier behavior. And more importantly, it supports both binary and multi-class classifiers, making it a flexible and scalable solution for various applications. Our methodology is as follows. First, we use a vision language model, specifically GPT-4, to automatically extract a large set of domain-specific attributes. Given a small set of images from a domain, like facial images, we prompt the VLM to generate a rich semantic corpus of hierarchical attributes. Next, we introduce Diffx, a training-free beam search-inspired algorithm that uses the semantic hierarchy to efficiently pinpoint the most influential attributes. It works by starting out with broad-level semantic groups, like eye features or mouth features, and generating counterfactual images using a diffusion-based editor. Specifically, we use Lattice++ to generate the counterfactuals, but our method can adapt to any editing pipeline. Each attribute is scored based on the change in prediction resulting from the edits, and only the highest scoring candidates are retained. We then move to more specific fine-grained attributes, like a mustache or wrinkles, and repeat the process. At each level, only features that meaningfully increase the classifier score are retained. This process helps us focus on the most important features without having to test every single one. These influential attributes are then ranked based on how strongly they affect the classifier's output, helping us identify the most critical semantics driving the decision. Note, more details regarding the methodology can be found in our paper. We will now share some of the results generated by our method. This visualization highlights the top facial attributes identified by Diffx for a perceived age classifier. For each attribute, the edited images and their respective subtypes are displayed in a hierarchical structure, outlined with a black border. The original images are outlined with a red border. The score for the young label is shown in the top left corner of each image. These are the top attributes identified across various animal domains, including bird, wildcat, and pet species. And these are the top attributes for the food domain, places domain, and fashion domain across various classifiers. Additionally, Diffx explains classifier decisions by analyzing the combined influence of joint attributes. In the example shown on this slide, results from the facial domain are presented, with the perceived age score for the younger label displayed in the top left corner of each image. These examples illustrate how specific combinations of attributes can either amplify or alter the classifier's predictions. The results on this slide showcase some comparisons with StyleX, which was the method introduced in the Explaining in Style ICCV 2021 paper. The table above contains a list of the top attributes discovered by Diffx versus StyleX. As seen in this table, Diffx is able to find more influential semantics across various domains. The figure below the table visually shows Diffx's ability to find influential attributes in the leaves and retina scans domains. To quantitatively assess Diffex's ability to find high-quality and disentangled edits, we conducted a user study with 50 participants on Prolific to evaluate the visual quality and disentanglement of attribute edits in the face and bird domains. Participants were shown pairs of unedited and edited images for 10 attributes and asked to rate how well the edits reflected the intended attribute and whether the changes were isolated using a scale of 1 to 5. As shown in this table, the results indicate that our edits were both visually faithful and well disentangled across various domains. To quantitatively compare Diffex with existing explainability methods, we conducted a user study with 35 participants on Prolific, focusing on semantic explanations in the bird domain. Participants viewed original and edited images alongside outputs from GradCam, Stalax, or Diffex, and were asked to select the attribute that best explained the visual change from multiple choice options. As shown in this table, Diffex significantly outperformed both GradCam and Stalax in helping users correctly identify the intended attributes. Overall, our method provides a way to explain classifier decisions through diffusion-based counterfactuals, which are image edits that reveal what features influence model predictions. We start by using a vision language model to construct a rich, hierarchical semantic corpus, capturing attributes across different domains. Then, we introduce Diffex, a beam search-inspired algorithm that efficiently ranks the most impactful features influencing the classifier. By combining semantic understanding with powerful generative models, our approach promotes transparency and helps build trust in AI systems.